Hello everyone, my name is Karen Wolff and my postdoctoral research looks at engineering problem solving across engineering sectors. The key drive has been to identify what it is that we're doing or should be doing in higher education to deliver the problem solving engineering practitioners we so desperately need. I'm particularly interested in the relationship between the disciplines underpinning the curriculum and how they play out in real-world practice. Today, I'm going to be foregrounding mathematics in engineering practice. I'm going to start by sketching the original problem and the theoretical framework for the PhD study, as these findings led to the current postdoctoral study. Now, the focus is mathematics in engineering problem solving and the patterns that have emerged. The heart of the paper is the question of mathematical thinking, and I'm going to share with you some exploratory work using autonomy to examine how this plays out in one particular case study. The starting point for the original research was the dropout rate on engineering programs and employer feedback on graduate inabilities to apply knowledge. Having worked as a lecturer on a mechatronics engineering program and having access to industry partners on an ongoing basis, I was acutely aware of the increasing complexity in this field, particularly in relation to dynamically evolving technologies. More than one employer commented on the disjuncture between what we had in the curriculum and what was really required in industry. And I saw the problem as inadequate understanding of the nature of and relationship between different forms of disciplinary knowledge in 21st century engineering problem solving. Now let's take a look at the original research site, mechatronics engineering. Now mechatronics is the computer-based control of an electromechanical system. Your microwave oven is an example, an ATM, but so too the automation systems you find in any factory. Mechatronics practitioners work in everything from manufacturing to medical and agricultural sectors. And in all these sectors, they're applying very different forms of disciplinary knowledge. Theoretically, the work is located in what Bernstein terms the field of recontextualization. Now, this is effectively the space between concepts and contexts. The concepts captured in the curriculum are recontextualized through the curriculum text, then pedagogy, and into practice. Now, if employers are complaining about graduate inability to apply theory, then on the one side of the equation we have that theory, and on the other side we have application. And if I wanted to understand the gap, then I needed languages of description or translation devices to unpack these. Now, the first language of description is Bernstein's characterization of knowledge structures. This is based on how knowledge progresses in the field of production, but I've used these as starting point indicators of the different organizing principles in a typical mechatronics curriculum. Now, on the right-hand side, color-coded in green, you will see areas underpinned by physics. This is what Bernstein terms a hierarchical knowledge structure, meaning concepts build on each other, subsuming or absorbing lower-order concepts. Now, mathematics is what he terms a horizontal knowledge structure with strong verticality and grammaticality. This means there are different mathematical languages, each with its own internal and external rules. There are concept chains we recognize as mathematical, but there are several mathematical languages. Now, in contrast, we have horizontal knowledge structures, also with many languages, within the same kind of discipline, but they have very different rule features. They borrow from each other. There's a great deal of redundancy and change. Just because you use one term or one principle in one kind of language does not mean you use the same in another. This is like art or sociology, but it's also the feature which underpins information communication technologies. So the discipline I've labeled here as logic, from logic-based systems. In engineering, this is what we call control systems. Now, these three disciplinary structures represented by physics, mathematics, and logic are acquired in different ways, and they have implications for teaching, learning, and application. So I wanted to see how these three played out in real-world problem solving, but I needed a second tool to help me bridge that space. Using Herbert Simon's distinction between the inner and outer environment of an artifact, or in this case, a problem site, a physical problem site, I established 4 key elements in the knowledge practice environment that each case study constitute each case study. There is a problem solver in a problem environment facing a problem structure made up of those 3 disciplines: physics, mathematics, and logic. And this problem solver needs to solve a problem. In other words, undergo a problem-solving process. Now, the overarching tool to help me analyze this comes from specialization, the LCT dimension, but a specific aspect, epistemic relations, which is represented as the epistemic plane. Now, quite simply, this enables us to look at how we approach what. The vertical axis refers to the boundedness of a phenomenon, where strong means a phenomenon is recognized or accepted by the field as having a particular nature, and weak means the phenomenon is unclear or ambiguous or contested or open. The horizontal axis, the discursive relations, is how we approach that phenomenon, from fixed, bounded ways on the right-hand side to open or multiple ways on the left-hand side. Now, this plane gives us 4 quadrants. In the purest quadrant, we have a specific principle and associated procedures which everyone would recognize, such as voltage calculations in a system. The doctrinal quadrant, the bottom right, is where it doesn't matter what the phenomenon in question is. What matters, or what is foregrounded, is the method, such as using the scientific method or applying Six Sigma or lean manufacturing. The situational quadrant at the top left is where the phenomenon is quite clear, but there are a number of approaches, like deciding on a control system. Now, the fourth quadrant is either because there is no clear phenomenon or approach, in other words, no insight, or the practice being observed or articulated is not about knowledge, but rather about knowers in the system. Now, each of these 4 quadrants represents a code, a way of thinking. And using these tools, I went into 3 different types of research sites, having selected 18 participants based on an initial problem-solving questionnaire to 50 volunteers. I looked at how each practitioner approached, analyzed, and solved a particular problem. And I color-coded their texts, their in-situ interviews where they took me through the problem in relation to the actual artifact. I color-coded those implicit, or explicit references to physics, mathematics, or logic. Now, this gave me a whole range of problem-solving maps across different kinds of sectors. From contained systems environments, these are small businesses focusing on research and development or standalone devices, to modular systems environments. These are either people who build or connect machines and subsystems, to distributed systems environments, found primarily in manufacturing, where the focus is not on the machine or the device itself, but on the production process enabled by those machines and systems. Now, although I had red-coded color spots everywhere, in other words, the mathematics, very few of these were explicit mathematical references. They were all implied. And unlike the physics, for example, they occurred in all quadrants. Let's just take a look at these examples. Now, these are moments within those particular problem-solving case studies where the mathematics is revealed from a situational insight perspective or a purist insight perspective or doctrinal, and in this bottom left, in multiple quadrants. Here are those examples, the actual textual examples from which those graphs were drawn. Now, as you can see, we know the mathematics is in service of something else. in this purest quadrant, the example is clearly in service of a physics principle. In the left-hand quadrant, the graphs that this practitioner refers to are performance maps, the graphic representation of speed or efficiency over time. In the doctrinal quadrant, we see the same principle of efficiency, but in production language. Now, although I've pointed out what the mathematics may look like, these practitioners are not explicitly talking the mathematics we would recognize in the curriculum. So let's separate these two things out. Let's look at how they talk maths. And I'm going to use this example in the Noah quadrant. Now, this is a very interesting problem, where a persistent error by operators led to the installation of what I'm going to call a policing device, a camera checking system. Now, before I take you through the problem, we need another tool. We're going to experiment with autonomy. Now, as with the other dimensions, here too we can see two things set in relation to each other. Any set of practices or ideas is made up of constituents that are arranged in a particular way. This sets up two relations: positional autonomy between positions from within a context and outside that context, and relational autonomy between principles from within that context and those from elsewhere. First of all, we have to define what our target is. What is the sphere that determines this in-out location and principles of practices? In our case, the sphere or context is engineering problem solving, and the target is mathematics in that engineering problem solving context. Now, what this means is that in our sovereign quadrant, we recognize mathematics used for purposes of solving a mathematical aspect of the engineering problem. In the Roman quadrant, we see the use of practices from elsewhere for purposes within. In other words, this context might not facilitate the explicit use of mathematics to solve the problem, so other languages are used, languages possibly derived from that context itself. Now, because our focus is mathematics in the engineering problem-solving context, in the Trojan quadrant, we would see the use of practices from within for other purposes. In other words, here we might see the mathematics that you might find in an engineering problem-solving context used for other things, to make things sound scientific, or applying mathematics gratuitously. Finally, in the exotic quadrant, we see the use of practices from elsewhere for other purposes. So neither the principles nor the purposes of a particular practice appear related to solving the problem mathematically. Now, what we find is that the practices on the right-hand side are closer to the engineering problem itself, while those on the left-hand side speak to or about the environment. Now, I'm going to take you through moments of this actual problem. What I've just done is shown you examples of maths, but they never actually explicitly emerge in the case study. We see context-specific languages and practices. Okay, so here we have a case where operators are inserting a roll of stickers into a printer which is not calibrated correctly, and then the printer prints a roll of stickers with chopped off heads. So they call a maintenance technician who edits the actual sticker content on a computer and brings the barcode and the text too close to each other so that they'll all fit onto this misaligned sticker roll in a printer which is not calibrated correctly. These items with this barcoded sticker stuck on it are now sent to the client, who is very far away, and that client's scanner scans this sticker on the component and rejects the part because it can't actually read the barcode. So the manager or management at our company tells our research practitioner to install a camera system to check that the barcode dimensions are accurate. He purchases this, and he tells us that how it works is an optical sensor is aimed at the space between the barcode and the text, And if it's all white, as it should be, it converts that signal back through a computer system to a digital signal, which is 24 volts. If the beam reflected back has got black in it, it converts that signal to 0 volts, in other words, off. In other words, it doesn't record it as correct. So if we represent this mathematically, what we can see is that we're talking about angles and light rays over here. Here you can see the geometric reflection of what that would look like. Now he positions this camera system at a certain point on the checking bench, where the operators are now going to check that the barcode is in the correct place and the text is in the correct place on the sticker on the component. And he tells us, though, that you can't give the system actual measurements. That measurement is 1.25 millimeters. You can't tell it in the digital system, in the computer side of it, that it's got to be 1.25. You can only give it a voltage range. So what in fact ends up happening in this conversion from an angle through an analog signal to a digital is that you literally sit there with a ruler measuring between 1.25 and 1.5 millimeters, and then it's like toggling a switch and you say, yes, that's correct, that's now 0 volts, or that's 24 volts, and this is 0 volts. Now this system that was installed really slowed down the process. Yes, they did not have barcoded labels that were incorrect, but it really slowed down production process and led to a lot of frustration on the part of the operators working the system. Nevertheless, I have just taken you through that whole problem and shown you what the mathematics may look like, but that never explicitly emerged. What you can see, though, when you zoom into this principle is features dictated by this kind of environment. Note the passive voice that is typical of production processes. The printer is not calibrated correctly. The squashed barcode labels are stuck onto the parts. The sensor is positioned at a fixed distance from the checking bench. This passive voice, very typical of these kinds of processes. Note, for example, the language indicating the hierarchical organizational structure in this space, the operator and the maintenance technician and the client and management. Then we have references to equipment. All of this equipment could be generic. They could fit in anywhere. There's a printer, there are stickers, there's a scanner, there's a sensor, there's a steel ruler. Now, remember, we have a very specific target, mathematics in engineering problem solving. But the mathematical elements are disguised in that production language. In other words, here I suggest one sees this Roman code dominating. And across the reenactment interview, there were several journeys into the exotic. Here is an example in relation to why the operators do not calibrate the printer or insert the rolls correctly. And I quote, "Operators do not always understand or care for the value of some machine parts. There's a lot of company politics and an it's not mine so I don't care attitude." And we have a dash of physics and logic. Now, if we contrast this with physics and logic, for example, in the same case, the discourse announces itself as the discipline. Now, in other case studies, it's easy to spot the physics. Here we have the same practitioner talking about voltage in 3 different ways. A straight Ohm's law calculation in the sovereign quadrant, a circuit board personification in the Roman quadrant, which I found really, really interesting. Note he says, and as soon as the voltage goes below that threshold, it says, "Oh, Sherbet, I must quickly save the position that I'm in before the power goes down so that when the power goes back up, I know what position I was in." And although not strictly Trojan code, he does stretch voltage science into talking about quoting for a particular job. He says, in order to quote on a job, The power cables have to have the voltage drop calculated to ensure that the instrumentation has the right voltage, which specifies the size of cable required. Now, the point is that it's easy to find and analyze the physics and logic in these case studies, but the mathematics screams in its absence, and yet it is the single largest cause of dropout and failure on engineering programs. And I would like to suggest that we need to look at the mathematics in a different way. I thought, what if my definition of mathematics is actually being constrained by the curriculum? What do we really mean by mathematics in engineering? So I had to go outside of engineering in all the professions and start with mathematics itself. What do I actually mean when I say mathematics? Now, mathematics is the science of patterns, and the different branches reveal different patterns. If we take a look at some of these examples, geometry, clearly the pattern is shape. Calculus is about motion. Logic is about patterns of reasoning. Probability, and we've all seen these kinds of graphs at more quantitative studies, is about patterns of chance. Topology is about closeness and position. These are different mathematical languages. And remember we spoke earlier about Bernstein's characterization? Here there is evidence of it being a horizontal knowledge structure with so-called strong verticality and grammaticality. Nevertheless, now patterns can be modeled. A model is a representation of a structure in a given system. Now, the structure of a system is a set of relations among its objects, and each of these defining elements has certain features. Objects have properties, roles, behaviors. If we just took the theorem of Pythagoras in its a squared plus b squared equals c squared format, we see each of those, the a, the b, the c, have properties. They're squared. The role is in relation to each other, which takes us to step number 2, establishes a link. That a squared plus b squared is on the one side, and there's a dependence here. There are elements of causality. Now, those links and relations of dependence or causality give us the composition of something. There are internal links and there are external links. That gives us a certain kind of configuration, and that configuration occurs in a certain location. This then gives us a kind of structure, and to go back to our a squared plus b squared equals c squared, we see a geometric structure of a right-angled triangle. A systemic structure represented by all the graphs that you could insert establishing relationships if you're just using Microsoft Office, for example. You have kinds of structures that indicate interaction. You have kinds of structures that are temporal structures. So here we have an overarching concept that establishes how we might see mathematics as the structure of a system with objects that have relations. Now, if we take this definition into our actual problem-solving case study that I've just cited, perhaps we can see something different. One class of objects in our system is the people. They have roles and behaviors. Now, we already know that they do not fulfill their given roles, such as inserting the sticker roles correctly, such as calibrating the machine. This takes us to step 2, relations. The objects are linked and have relations of dependence or causality. The operator who does not calibrate the printer, or the technician who tweaks the barcode dimensions, cause the client's scanner to reject the parts. This takes us to the system, in other words, which describes the relationship between those objects. The client represents an external link. The two subsystems have hierarchical management structures, which has implications for how things are done and the time that this takes. And they're located far from each other, which has implications for cost. Now, analyzing the case study in this way, we see that the entire problem can be mathematically described, since mathematics is the science of patterns, which can be modeled as representations of the structure of a system. Now, what I've just done is I've operated in the Roman code. I've taken us out of mathematics and I've used a systems language to describe the mathematical features of our case study. And as we see, the case study in question could be mathematically described as broken links, misunderstanding of dependence and causality, and an inability to see the structure of the working system as a whole. And all of this starts from one simple axiom, that for any 2 points there exists a line. And I found the following quote really insightful for this research. And I quote from Borovich: Euclid and geometers for 2,000 years after him did not mention explicitly the betweenness properties of points and lines on the plane, relying instead on the intrinsic mathematical algorithms of their brains, which handled betweenness with remarkable efficiency. I believe it is the interrogation of this betweenness that is missing in our current approach to teaching mathematical thinking. This is precisely where LCT comes in. Now, in my work to date, legitimation code theory has helped to interrogate this betweenness, between concepts and contexts, between codes, between ways of enabling access to those codes, both semantics and specialization, and now, going forward, autonomy. I'm going to leave you with one last thought. Mathematics should be about notions, not notations. And I think this is the secret to really grasping at a conceptual and contextual level that the whole is greater than the sum of its parts. I thank you very much.